I'm Dr. Prakash Sharma from ABS Engineering College, Ghaziabad. In this lecture series, we are covering Unit 4 of Fundamentals of Mechanical Engineering, that is, Introduction to Fluid Mechanics and Applications. This is lecture number 2. In lecture 1, I've discussed the properties of fluids, Newton's law of viscosity, Newtonian and non-Newtonian type of fluid. Now, in this lecture, we will be covering Pascal's law and continuity equation. So we'll start with Pascal's law. What is Pascal's law? The Pascal's law states that the pressure or intensity of pressure at a point in a static fluid is equal in all directions. We can also say, like according to Pascal's law, the external static pressure applied on a confined liquid is distributed or transmitted evenly throughout the liquid in all the directions. So Pascal's law is expressed as follows. F is equal to P into A, where F is applied force while P is transmitted pressure. The A represents the cross-sectional area. So consider an arbitrary right-angled prismatic triangle that is submerged in the liquid of density rho. Here, this is the right angle prismatic triangle and consider that is submerged in the liquid of density rho. Since this prismatic element is very small, every point is considered to be at the same depth as the liquid surface. Therefore, the effect of gravity is also same at all the points of this prism. So, consider three faces, the area of the faces. First, we are considering the face P, P, Q, R, S. The small p is the dimension of PQ and the small s, this small s is the dimension of QR. So if we are considering the face PQRS, the area of PQRS is P multiplied by S. Similarly, the area of PSUT, the area of PSUT will be equal to Q multiplied by S. Similarly, the area of QRUT, the area of QRUT will be R multiplied by S. So here it is written like the area of is PQRS, PSUT and QRUT of the prism is PS, QS and RS respectively. Also assume the pressure applied on the liquid on these phases is P1, P2 and P3 respectively. Like P1 is the pressure applied by the liquid on phase PQRS. Then P2 is the pressure applied by the liquid on phase PSUT. And P3 is the applied pressure by the liquid on phase QRUT. Exerted forces by this pressure to the faces in the perpendicular inward direction. That is F1, F2 and F3. The angle is given as theta in the prism, and if we are breaking the components of F3, one is F3 sine theta in x direction, F3 cos theta will be in y direction. So when we are calculating the forces in these three phases, first F1 is equal to P1 into area of PQRS, and the area of PQRS is PS. So F1 will be equal to P1 into PS. Next, when we are calculating the F2, that is the force exerted by the liquid on the face PSUT. So the P2 is the pressure and area of PSUT, that is P2 into QS. Next is F3. F3 is the force on phase QRUT. So F3 will be calculated as P3 multiplied by area of QRUT, and the area of QRUT is RS. So F3 is equal to P3 into RS. So from the here we have calculated the forces, all three forces on three faces, on the three faces of this prismatic triangle. So now we are considering the triangle PQT. This PQT. Theta angle is given. Theta angle is given. Angle PTQ is given as theta. This. So in triangle PQT, what is sine theta? Sine theta is equal to P divided by R, and cos theta is equal to Q divided by R. So here we calculated sine theta and cos theta by using the triangle PQT. So the net force on the prism will be equal to 0, as this prism is in equilibrium condition. When this is in equilibrium, it means the net force on the prism will be equal to 0. So we equate the forces in x and y direction. First, in x direction, F3 sine theta will be equal to F1. This F1, when we are considering x direction forces. It is in equilibrium. It means the force in x direction and y direction will be 0. So first in x direction, F1 will be equal to F3 sine theta. And when we are considering y direction, F3 cos theta is equal to F2. This force F2 in upward direction and F3 cos theta in downward direction. When we equate this, the force in y direction will be 0. So that is the condition of equilibrium. X and y direction forces will be 0. So F3 sin theta is equal to F1 and F3 cos theta is equal to F2. Now we will put the values of F1, F2 and F3 from here. F1, F2 and F3. We put these values in this force equations. So when we put the values of F1, F2 and F3, we got some equations like P3 into RS into PR is equal to P1 into PS. That is for x direction. We put the value of F3 and F1. And when we put the value of F3 and F2, we got P3 into RS into Q by R is equal to P2 into QS. So from here, R is cancelled here, then S is cancelled from here, then P is cancelled by this P. It means P3 is equal to P1. This is written here. P3 is equal to P1. Then R is cancelled by this R. Then S is cancelled by this S. And Q is cancelled by this Q. It means P3 is equal to P2. This is P3 and is equal to P2. Now P3 is equal to P1, then P3 is equal to P2. It means P1 is equal to P2 is equal to P3. Means all the pressure on three faces is equal to 0. Therefore, the pressure throughout the liquid remains same. Therefore, the pressure throughout the liquid remains the same. This is what Pascal's law states. So there is two applications of Pascal's law. One is hydraulic lift and the another one is hydraulic jack, where the pressure throughout the liquid remains the same. This is all Pascal's law. Next topic is continuity equation. The continuity equation expresses the fundamental principle of conservation of mass. According to the continuity equation, the product of the cross-sectional area of the pipe and the velocity of incompressible fluid at any given point along the pipe is constant. So consider this following diagram. Consider this diagram. Now consider the fluid flows for a short interval of time in the tube. Assume that short interval of time as delta t. So in this time, the fluid will cover a distance of delta x1. This is delta x1. This is the lower end of the pipe and this is the upper end of the pipe. So in this short period of time, delta t, the fluid covers a small distance, that is delta x1, with the velocity of v1. The velocity of v1, by this velocity, the fluid is covering delta x1 distance in delta t interval of time from the at the lower end of the pipe. This lower end of the pipe. The A1 is the cross-sectional area of this lower end. Similarly, x2 is the distance covered by the fluid at the upper end of the pipe with the velocity v2, and the cross-sectional area of the upper end of the pipe is A2. So, in this time, delta t time, the distance covered by the fluid will be delta x1. Delta x1 will be the distance covered by the fluid in delta t time. That will be equal to v1 into delta t, velocity into time. The velocity is v1 and the time interval is delta t. Now at the lower end of the pipe, the volume of the fluid that will flow into the pipe will be volume is equal to A1 into delta x1. So we will put the value of delta x1 from here. So volume is equal to A1 into v1 velocity, small v1 into delta t. It is known that mass is equal to density into volume. We all know that m is equal to rho into v. So the mass of the fluid in delta x1 region will be, mass is, we denote this mass in delta x1 region will like delta m1, which is equal to density into volume. So density is here is rho 1 and volume we have calculated here A1 V1 delta T. So rho 1 into A1 V1 delta T. This is equation 1. So for the lower end with cross-sectional area A1, I have already told that the cross-sectional area of lower end is A1. So when we calculate the mass flux will is equal to delta M1 by delta T. So delta M1 by delta T, mass flux is equal to rho 1 A1 V1 at the lower end. Similarly, for the upper end, mass flux will be rho 2 A2 V2. This is equation number 2. This is equation number 3. So what is rho 2? The density at upper end. V2 is the velocity of the fluid through the upper end of the pipe through x2 distance, delta x2 distance in delta t time, and A2 is the cross-sectional area of the upper end. So mass flux at the lower end of the pipe is equal to the mass flux at the upper end of the pipe. That is, we equate the equation number 2 and equation number 3. What are those equation number 2 and 3? This is mass flux at lower end, equation 2. Mass flux at lower upper end is equation number 3. We equate these equations. Equation number 2 is equal to equation number 3. It means rho 1 A1 V1 will be equal to rho 2 A2 V2. In simple form or in general form, it can be written as rho into A into V is constant. So, if the fluid is incompressible, the density will remain constant for steady flow. So, rho 1 is equal to rho 2. So, this equation 4 can be written as A1 V1 is equal to A2 V2 when the fluid is incompressible and the density of the fluid remain constant for steady flow. It means A into V is constant. Area into velocity is constant. Now, if R is the volume flow rate, the above equation can be written as R is equal to A into V, that is constant throughout the pipe. R is the volume flow rate, that is constant. A into V is constant. This is the continuity equation. These are the references given here. This is all in this lecture. Further topics will be covered in the further lecture videos. So, we have discussed the Pascal's law continuity equation in lecture number 2. Further topics will be covered in next lecture. Thank you.